Well, ladies and gentlemen, we're going to be going over the last 2 pages of the test review. Try to get that done quickly. A lot of stuff. I may just say it's on this page of your notebook. Look there. And it's there. So let's see. Number 23, covalent bonds. Whoops, let me get that focus up there. Better zoom out. Okay, covalent bonds are made. Look on the front of your packet, as it shows you that covalent bonds are made with nonmetals bonding to nonmetals. Also, covalent bonds are when nonmetals share a pair of electrons, or maybe even 2 pairs of electrons, or even 3 pairs potentially. So that's that one. Number 24, what happens with electrons when an ionic bond forms? So an ionic bond, you've got metals like lithium, with lithium has its 1 valence electron. It is going to throw its electron away, and nonmetals like fluorine, sitting there with 7 valence electrons, will happily take it. So electrons are given and thrown away from another. Metals form. Okay, well, just like we talked about here on this cover here, metals will always form. When they throw away that negative charged electron, they become a positive ion. Every metal, all of these dark ones, when they ionize, they become a positive ion, and the nonmetals become negative ions. So metals form positive ions called cations, and nonmetals form negative ions called anions. What's the chemical formula when calcium, Ca, calcium has 2 valence electrons because it is in group 2 of the periodic table, bonds with oxygen? Oxygen is in group 16, or the old 6A. So oxygen is going to, let's see, first off, calcium is going to throw away 1 electron and give it to oxygen, and it'll throw away its other oxygen. This is a perfect 1-to-1 ratio. It only takes 1 calcium throwing away 2 electrons for oxygen to gain those 2 electrons. Is this ionic or covalent? Well, calcium is a metal. Oxygen is a nonmetal, so it is ionic. That's one of the definitions of ionic bond. Coming back to here, metals bonding to nonmetals, or electrons being given or taken. So oxygen is taking the electrons, calcium is giving them. List the characteristics that include melting point, conductivity. Well, you know what? Our starter today, starter number 12 today, we went over those. I'm not going to go over those again. It's going to take too long. You can go to starter number 12. And we had here at the bottom, starter number 12. Ionic compounds have a very high amount of energy, a lot of heat energy needed to melt them. Covalent compounds like sugar, when we did the lab, they melted almost right away and burned quickly. Ionic compounds tend to be crystal solids at room temperature. So we just think of salt as just one of the greatest examples of an ionic compound. Covalent compounds like water, like wood is a very common covalent compound. Gas would be like air, the oxygen and nitrogen molecules in air, and liquid, water, H2O, those are all covalent compounds. Since it takes less energy to melt them, to burn them, to make them react, they can have solids, liquid, or gas states of matter. And lastly, ionic compounds, when they can conduct electricity if they're dissolved in water, or if they're melted, they can conduct electricity. Covalent compounds, we had that the sugar and our rubbing alcohol had no conductivity. We had a mixture of starch, very, very low. They are too busy sharing and keeping their electrons together, where ionic bonds, they're throwing electrons around, and so it's easy to conduct electricity with that. Let's see. Number 28, when hydrogen forms a bond with a halogen. Okay, so here's hydrogen. Now we got this chart over here. Zoom out a little. What type of covalent bond is formed? Well, hydrogen, if you look at its electronegativity, it's 2.1. And let's see, a halogen, okay, here's a bunch of halogens. I'm just going to do fluorine because it's at the top, it has 4. So I'm just going to use fluorine with an electronegativity of 4. So when you, now the idea is you subtract these. If you take 4.0 and subtract 2.1, I think, let's see, is that going to be 1.9? I'm trying to remember. I think that's 1.9, isn't it? Let me make sure. 9 plus 1 is 0. And then we have, I think I got that right. Yeah, my brain isn't working right because it's, yeah, 1.9. There we go. So anyway, when we look at this chart, 1.9 falls in this category right there, which tells us that, yeah, a metal bonding to another nonmetal is covalent. They're going to share electrons, but what it's telling you when you look on here, that it's going to be, there's going to be a partial positive side and a partial negative. Oh, there was an example right there, hydrogen fluorine. So this is where fluorine is like the polar bear and hydrogen is like the penguin. They're going to share electrons, but the halogens will hog them, or any of the elements over here will tend to hog the electrons. Let's see, number 29. Describe the bonds in molecules in solids, liquids, and gases from weakest to strongest. It takes the most force to keep things locked into a pattern. So this is the most. And then liquids would be the middle. And then gases take the least energy because gases are flying over. They're not really pushed together. It takes the least energy to be a gas. Now, they have a lot of kinetic energy because they're moving, but to get a gas locked up to become locked into a pattern, boom, like a solid, it takes a lot of energy to do that. What is the electron configuration for nitrogen? Well, let's see. In your packet, I asked you all to do some of these, and let's see. I'm going to your packet. You might want to pause this for a moment. We did this activity. There we go. Oh, was it this one? No, it's the last page, Richard. There we go. So we did this in class, or we started to. Nitrogen has got 7 electrons, 1s2, 2s2, 2p3. You can use the slanted diagram to show you the order that you have to put those in, or you may use your off-bow diagram, which we will have on the test. You can start filling in the electrons and then start reading off the electron configurations. For sodium, we had this electron configuration. For silicon, I don't know if we did silicon on this one. Silicon has 14 electrons. And let me look on my periodic table. Yeah, silicon, 14 electrons. So 1s2, 2s2, 2p6, 6, 7, 8, 9, 10. Oh, now see, I don't have it memorized. What's after the 2p? 3s with 2. Now we're at 6, 8, 10, 12. We need 2 more electrons. After the 3s, we're going to fill the 3p, but I think we only need 2 there. So let me make sure. 6, 8, 10, 12, 14. There's the electron configuration for silicon. And then chlorine has 17 electrons. So it's going to be very similar. I don't think we did chlorine on this one. No, I didn't have you do that one. So 1s2, 2s2, 2p6, 3s2. I'm just kind of copying what we started here. Now 3p, I think it's going to be 6. Now we need a total of 17 electrons in chlorine. Let's see, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ooh, 17, 18. I want 1 too many. This should be a 5, 3p5. Now we're good. And that kind of makes sense because chlorine on the periodic table lives right there, and it's 3p, 1, 2, 3, 4, 5 is where chlorine. So that's kind of a cool way to use that little chart. What elements have these electron configurations? Well, first off, you just need to count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25. And on the periodic table, the element that has 25 electrons is manganese, Mn. This one over here, let's do it. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. And the element that has 20 electrons is calcium. Use the off-bow diagram at right. What element is shown? Okay, so we've got this kind of modified off-bow diagram. Oh my goodness, my copy didn't come out very well. Let me grab another one here. For some reason, they don't print right when I do it that way. Okay, so we got this one there. So let's see. Let's just count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 31. So there's 31 electrons. You look on your periodic table, the element with 31 electrons is gallium. So that's how you do that one. Okay, what elements have these electron configurations? Add up the electrons. 1, 2, 3, 4, 5, 6, 7. And I believe atomic number 7 is nitrogen. Okay, we have 4, 5, 6, 7, 8 electrons. Okay, well that's going to be oxygen. And then over here we have 5, 6, 7, 8, 9. And that looks like that's going to be the element fluorine with 9 electrons. What is the electron configuration of O -2? Well, oxygen, first off, oxygen has 8 electrons total. And since it's a -2 electron, I'm going to do its Lewis structure, 1, 2, 3, 4, 5, 6. Oxygen's going to gain 2 more electrons to be a -2 ion. So oxygen ion is going to actually have 8 plus 2. It's going to have 10 electrons. So its electron configuration for oxygen, I'll just do it on the chart here, 2, 4, 6, 8, 10. So that would be the electron configuration right there for oxygen, 1s2, 2s2, 2p6. Oxygen 2 negative ion, okay? Because it thinks it's neon, but it has a negative charge. And then what was the other one? Magnesium 2 plus ion. Well, magnesium has this Lewis structure on it, and it's going to throw away 2 electrons. It's going to get rid of those. So magnesium normally has, where are we? Magnesium normally has 12 electrons, but it's thrown away 2 electrons. So now it only has 10 electrons. It's an ion. So let's see over here. 2, 4, 6, 8, 10. Wow, look at that. Magnesium 2 plus ion, it's going to have the same electron configuration as neon, because magnesium, when it loses those 2 electrons, it becomes 1s2, 2s2, 2p6. Find the second element. Okay, you know what? I'll do one of these, but I'm not going to spend time. The second element and symbol, period 4. Periods go across the table. The second element is calcium, Ca. Second element in period 5. Okay, I'm kind of having fun of strontium. Okay, done. This Sr. Let's see. The second element in group 13. Group 13, aluminum. And group 17, the second element, here's group chlorine. What are valence electrons? They're the outer electrons. If you come to science labs, I give you a really nice periodic table, and it shows you all the electrons, including the valence electrons. But you only get that when you come to science labs. Let's see. How many shells and valence electrons do the following have? Lithium it has 2 shells. Calcium has 3 shells because it's in period 4. 4 shells. I'm doing shells first. And then lead down here, Pb, it is in period 6, so it has 6 shells. Tellurium, now I got to find tellurium. I don't have that one. Is that down here? Oh, I'm embarrassed. I don't know where tellurium is off the top of my head. Yikes. Okay, just be calm. We'll find tellurium. Okay, tellurium, where are you, you turkey? I don't know where tellurium is. So, oh, there it is, right over here. It is right there, tellurium, and it's in period 5, so it has 5 shells. Chlorine is in period 3, so it has 3 shells, and argon also has 3 shells. Now, valence electrons. Okay, so you'd see what group they're in. Lithium is in group 1, so it has 1 valence electron. Calcium's in group 2. It has 2 valence electrons. Lead is in group 14. So now it's a metal. It can have 4. It can also have others, but we won't ask you exceptions. Tellurium is in group 16, so it has 1, 2, 3, 4, 5, 6. Chlorine is in group 17, so chlorine has 7 valence electrons. And argon, in group 18, it's a noble gas. 1, 2, 3, 4, 5, 6, 7, 8. It has a full electron configuration. Okay, let's see. What are ions? Okay, atoms that have gained or lost electrons. Atoms that have gained, lost electrons. Sorry, it's messy, but I want to get this done in a hurry. Give an example of a cation. All right, any metal that ionizes. Lithium, did that earlier. It loses that electron, it becomes plus. Iron we use quite a bit. You can have iron 3 plus or iron 2 plus. And a lot of times we'll call that iron Roman numeral 3 and iron Roman numeral 2. Let's see. Let's come on over here. Oh, we're on the last page. What are the following groups? Okay, look it. I'm not going to go through this. If you're having trouble remembering the groups, then you need to take this chart that we did and you put it somehow into your summary page, okay? So I'm not going to go over that. We've already done that. If you have put it in your summary page. But you draw or describe the periodic trends for atomic radius. Well, I've given that to you. I'm not going to draw it in there. Here is a chart. I've given it to you in there. There's the trend. They get smaller as you go to the right. They get bigger as you go down. Electronegativity. We did our graph today. Electronegativity. You can look at this chart. Highest up in this corner, lowest down here. As you go across a period, electronegativities get higher. Then in the next period, they get a little bit smaller. So as you go down the chart, every period they're getting smaller and smaller. But as you go to the right, they get bigger. We had ionization energy. We plotted that one out. Okay, we made this really nice graph in class. This is the energy needed to remove an electron. Electronegativity was how badly they want one. Fluorine really wants electrons. Chlorine really wants them. Helium doesn't. And ionization energy, as you go across the table, this is the energy to remove an electron. As you go across a period, it gets higher and higher, and it's highest at the noble gases. And when you start a new period, it's a little smaller, but as you go across the period to the noble gases, group 18, it gets larger. So there it is. What are the trends for the atomic size as you go down the periodic table? Okay, you know what? There it is. You find it out. Oh, we got an announcement going on here. Okay, let's see. The next one. How does size change as you go across? Okay, again, look there. What group of elements are the peaks when it comes graphed by atomic number? Okay, you know what? So when we go across here, if we were plotting this off, the alkali metals are the largest in a period, and then as you get to the noble gases, they're really small. So the peaks on atomic radius would be, let's see. Oh wait, let me get the wrong. I got the wrong chart here. Let me get one that's a little bit better graphics. Oh no, I lost my paper. I had a nicer. Okay, I'm gonna have to live with this one. Shoot, I had a better copy to use. Oh, is it over here? There we go. This is the full one over here. So for atomic radius, this is going to be the left side of the periodic table and gets smaller. So this will be the alkali metals. These will be noble gases. Okay, let's see. You know what? You can look on. I'm not going to spend time going. You can look on this but we've got it. Alkali metals have the highest size. Noble gases get smaller and it resets. What's the next one? Peaks. Okay, I'm done with atomic size. What are the trends for electronegativity? Here's the graph we did. Okay, as you go across the table, they're gonna get bigger, and then but 0 at the noble gases. Noble gases have no electronegativity. What elements are the peaks for electronegativity? We said they were the halogens, because I think this was going to be fluorine, and that was chlorine. That's as far as we got in our graphs in class. What groups are the lows? Okay, well, the lowest electronegativity will be the alkali metals. There's going to be lithium, there's going to be sodium. But the alkali metals have no electronegativity, so I guess you could say those are. Depends upon how the question's worded. What group of elements are not included on electronegativity? Well, that's going to be the noble gases because they don't have an electronegativity. They don't need to attract electrons. What are the trends for ionization energy? The energy to remove an electron? Well, they're highest with the noble gases. It's really hard to remove an electron from a noble gas. And then as you go towards the left side of the table, the metals, it's really easy to remove an electron from the metals over here that are easy to throw away. So let me see. What are the trends as you go across the table? For ionization energy, highest right there, lowest down there. Because the higher you get on the table and the closer to the right, the more energy it takes. So biggest energy to remove, and then still pretty big, still pretty big, still pretty big. And then as you go over here, it doesn't take much energy to remove those. They get tiny, tiny, tiny until there's almost nothing. All right, there you go. Bye.